Hey guys, this is Alan, back to talk a little bit more about op amps. And in this video, I want to talk specifically about the concept of rail voltages and amplification as they relate to the input voltages, or the voltages at the input terminals of the op amp. So looking at our slides, we've got one here that describes biasing voltages. This is slide 6, I believe. The biasing voltages to the op amp are often called the rail voltages. These rail voltages are built into the op amp. They're not something that we create or that we apply by doing something to the terminals of the op amp or anything like that. It's something that when the op amp is designed, these rail voltages are part of the design. If the op amp is said to be biased to 3.5 volts, that bias represents the difference in the rail voltages. So we may not know what those rail voltages in fact are, but we know the difference. If they are biased 3.5 volts, the difference is the 3.5 volts. The range of the output voltage, which is the gain multiplied by the difference of the input voltages, must be between these rail voltages. If not, the signal will be distorted during the amplification. Alright, so let's think about what this means and relate it to what we already know about. Let's go to our whiteboard and let's look at an important equation that describes what we just talked about. So on our whiteboard, we've got an equation here that says that the absolute value of the difference of the voltages at the input terminals of the op amp must be less than the absolute value of the supply voltage. That's what the VCC is. That's the supply voltage. No, that's not the signal. This is the power supply voltage, right? Which we often see as plus or minus 12 volts or plus or minus 15 volts, minus the voltage margin. Now, voltage margin is it's like a buffer zone. So what we just said didn't mention the voltage margin. It simply would have been VCC divided by the gain of the op amp. But in reality, every op amp is going to have a voltage margin, which you should be able to look up on a data sheet. And it's not something that you calculate. It is what it is, and it too is part of the design. But it's a buffer area that tells us, all right, don't let the amplification or don't let the output voltage approach even this close of the supply voltage, because if you do, then you're going to distort the signal and you're no longer going to be amplifying the signal and preserving the integrity, if you will, of the input signal itself, the waveform. So let's look at an example and hopefully it'll make it a little more clear. On slide 7, we have an example. We've got an amplifier with a gain of 80,000 and biasing voltage of 12 volts with a voltage margin of 3 volts. What is the approximate maximum voltage difference between the inverting and non-inverting terminals such that the output will not be distorted? Alright, so let's take a look at what we're given. We're given the gain of 80,000. So our gain equals 80,000. We're given a biasing voltage of 12 volts. Now the biasing voltage is not necessarily our VCC, but in this case we're going to say it is. We're going to assume that our rail voltages are 12 volts and 0 volts. So let's say our VCC, our supply voltage, is 12 volts, and it gives us a voltage margin or a buffer area of 3 volts. So VM, we'll call it, equals 3 volts. So basically, again, just backing out of the numbers in the equation for a second, what we're saying here is that because the supply voltage is 12 volts, we can't get within 3 volts of that. We have to leave, our output voltage cannot approach within 3 volts of the output voltage. Otherwise, you're going to distort the signal. So we know from previous videos and studies that the output voltage, Vout, equals the amplification, or the gain, multiplied by the difference, V2 minus V1, or V1 minus V2, whichever you like. And so this V out has to be, and we need it to be less than 9 volts. The 9 volts, perhaps I shouldn't have skipped that step, but all that is that's our 12 volt supply minus our 3 volt buffer area. All right, and again, these are absolute values that we're concerned with here. So don't worry too much about your signs or what you put first. So for our example, to solve that problem, our appropriate maximum voltage difference, which is our V2 minus V1, must be less than, we'll say or equal to, 9 volts divided by that amplification, where the amplification is, we'll go ahead and sub it in. We've got 80,000 is given to us in the problem. So that means that V2 minus V1, and we will use our, let's be accurate here, we'll use our absolute value symbols, must be less than or equal to, let's plug it in our calculator, and we get, where is my calculator? Let's do it together. Check me here, guys. 9 divided by 80,000, and we get 112.5 microvolts. So the corresponding answer that is closest on our slide is choice A, which is 113 microvolts. And there's our answer. So that is rail voltages and voltage margin and how those are related to the gain of the circuit. I hope that helps, and good luck.